Hi everyone, my name is Harshita and today I'm going to give a talk on Run ZFS in userspace. So I'm a developer advocate, kind of a newbie in that area, and a software engineer. So I work at a company called Maya Data. We basically work on containerized storage solutions for Kubernetes stateful applications. In simple terms, we provide storage in containerized form. And so today we are going to talk about these four bullets. First is what is UzeFS, why UzeFS, how we use it in our storage engine. Storage engine is called cStor, and the key components which are included in the storage engine. So what is UzeFS? So UzeFS is basically the modified version of ZFS, which comprises of the changes which we made in ZFS to run it in user space instead of kernel space, and also the changes which we require to make it or as a cStor replica. So cStor, as I mentioned, is a storage engine, and it basically comprises of three things, which is a zrepl binary. I'll come back to it. What is zrepl exactly? And the second thing is implementation of replica API, which we use for the IO operations plus the rebuilding, replication, cloning part of it. And the third thing is management binaries, the changes which we made in management binaries, ZFS and zpool. So why the UzeFS? Okay, so as we know that ZFS provides excellent advanced file system capabilities, and we tried to use the ZFS file system capabilities, which basically runs on an individual server, to make a storage engine which is containerized and which can be run on on-premise and multi-cloud platforms. And the benefits, or you can say perks of UzeFS is there's no kernel dependency as it runs on user space, completely in user space. Rebuilding, the extra feature or the feature which we provided is rebuilding, which is including the ZFS features which are already there, which is snapshot cloning, replication, and it is containerized, means it is loosely coupled and it's API driven. Now, before going into details how we used it and what changes we made, I'll just give you a basic architecture of the storage engine. So on the bottom side of it, there are disks, block devices, and we created a pool which is called cStor pool on top of it. And in this case, it is mirrored one. And on top of cStor pool, we create our volumes. And for the volume replication thing or a factor, we create a volume replica on each node where cStor pool is running. And that pool is managed by a target pod, which can be run anywhere. And now on top of it, we ran an application, stateful application, which uses a PVC to create a PV, and basically writes on a iSCSI device, which is on the node where that application is running. So basically, application will be running on any node, and on that node, a iSCSI client should be there, so that we can create a iSCSI device and communicate with the iSCSI target, where the iSCSI server is running. So when it comes to this, target receives block IO from the iSCSI client whenever application runs or writes anything on the device, and the target work is to replicate that block IO to the volume replicas, which are on all the three nodes, or any kind of node or any number of nodes, depends on what replication, how much replication factor you need. And the second thing is cStor replica, which receives the IO and basically writes on the local storage, which is our block devices. So how we leveraged UzeFS to build our storage engine. Okay, so first thing is ZFS zpool CLI. What changes we made there is, as we know that zpool and ZFS CLI works in user space, and they communicate with the ZFS which runs in kernel space. and it basically does a isctl call, which is a system call. But as our goal was to run our storage engine in user space, so what we did, the approach we took is isctl redirection, where we allow ZFS to not do the isctl call, but instead of create a Unix domain server. So the ZFS CLI is now runs on a Unix domain client side, and the useFS, or which we call useFS, or the zrepl binary, which where the ZFS is running in user space. On that side, Unix domain server is running. Yeah, so isctl redirection, as I told you, ZFS CLI Unix client is running. On the zrepl side, which is a binary where ZFS runs in user space, there the server is running. So instead of the isctl calls, we did the Unix system calls, not system calls, socket calls, and then these two components make the call. And now what happens is ZFS CLI will send a command. For example, to create a pool, we'll send a zpool command, and with the this information or command will be sent with the isctl information, and this zpool CLI runs on a container, as the whole system or storage engine is containerized. So these CLI binaries run on a cStor pool management container, which is kind of a sidecar for our cStor pool pod. And it sends the information with the commands and the IP address of the target. I'll come back to what is target and how we are using the target to do the IOs. Next is when the zrepl receives the information, it runs the same functionality or functions which ZFS runs in case of kernel space. Okay, so what is iscsi target? iscsi target is usually used to do the IO operations and syncing of the data over the replicas, and it communicates with the zrepl. So two kinds of connection are made. First is data connection to send the IOs. Second is management connection, which is basically used for the registration of the replicas. So for example, we created a zvol to and the zvol which was created will make a connection, management connection, to the target, and will register itself to the target, so the target is aware of what replicas are there. Yeah. So next thing is implementation of API. So the main thing is the changes which we made for the zpool to be able to run the zpool commands is isctl redirection. The second thing, to be able to use the zvol, we skipped the device creation part, because to create a device creation, you have to go into the kernel space side. So what we used is we used zvols to do the IOs and to do the replication and cloning and everything. So the IO operations received at the libstore side, which is basically a layer which runs on zrepl side to basically do the read write API specific calls. And we also created a wrapper of a DMU layer, which is a ZFS layer only, data management layer. And there we just created a wrapper so that we can send other IO operations along with the metadata. And what is that metadata is? Target with the IO operations send a metadata, which is kind of an incremental IO number, which is stored in our volumes in ZEP attribute, which is used to rebuild in case of a failure. So for example, if we talk about the whole flow, user created a cStor pool pod. How he will create it? There's a YAML, he provided the block devices, and he mentioned, I want a mirror kind of pool. Then cStor pool pods will come up, one on each node. Then on the container, cStor management container, zpool, ZFS binaries are running, and a command for creating a zpool will be sent to the zrepl, which is running on another container on the same pod, and it will ask to, create a zpool for me. A pool will be created then, And next thing is, after a pool is created, now we want to carve out the volumes. So the same binaries will send a zvol command along with the target address. Target address is the same thing which I told you, which is used to send the IO operations. So zvol will be created, and zrepl will make a connection to the target for the management connection to register the volume. And when the target sees, okay, the volume is healthy, and who tells the volume is healthy? The volume only tells or sends a signal, okay, I am healthy. And then IO operation will start coming from the application then to the iSCSI normal iSCSI device, which runs on the same node, to the target, then to the replicas. And yeah, so suppose so in case of volume replicas, when it comes up, every replica's state is degraded. Then it communicates with the target. Then target will tell, okay, start rebuilding yourself. Though how will they rebuild? Will tell as ZAP attribute contains the IOCTL, sorry, not IOCTL, IO number, incremental number. So the IO number is basically it's a number which is which we send incrementally along with the data, which is block data, which is approximately 512 bytes, and with the IO number which is the largest or the highest is the latest IO sent to the volume. So suppose volume 3 has the highest IO number, so it means the latest IO was sent to that replica, and target will tell, okay, this is the volume from which you need to rebuild. So the volume will start rebuilding, and once every volume is healthy, basically we use n by 2 plus 1 factor, which is suppose there are 3 volumes, at least 2 of them should be healthy for the IOs to come in. And then so basically libcStor is a library which we use to do the API specific operations on the volumes. Yeah, these are the API operations which are performed through the cStor API. And the components we talk about is the cStor target. I already told you what it is, and it exposes the iSCSI device, which is to the application. So as I told you, the iSCSI initiator should be running on the node where the stateful application is running. So it's the work of target to expose that disk to the application so that application can write on the device. And it also runs as a container, and it's also used to send the data and to sync. What I mean by syncing is every replica should have the same data. And yeah, cStor pool, it's logical storage pool which is comprised of the physical devices or the block devices which you mentioned while creating the pool. And yeah, pool pod is created on node and a set of devices. Now management container is the container where the binaries are running, and on the same pod another container where the zrepl is running, which is basically UZFS, which is a ZFS running on userspace. And yeah, as Unix domain socket or server is created on the servers on the zrepl side, and the client is created on the management binary side. And to directly contact with the developers who have done this thing, you can join the Slack channel, and there are blogs written by the developers, and there's a GitHub repo for our storage engine, which is cStor. Thank you. Any questions?
Thank you indeed. Sorry, we don't have time for questions anymore. If you have questions for Ashita, please find her somewhere else and ask her questions.
So if you join the Slack channel, your developers will be direct in touch with you, so they'll be better to answer the questions as they have write the code.
Thanks.